Okay, let us continue. As we know that characteristic equation, let's recall back. Characteristic equation is equal to 1 plus K GS HS equal to 0. So if you were to modify it back, it becomes KGS HS equal to minus 1. And then we know that minus 1 is equal to magnitude of 1 and angle of J R pi, where R is 1,2,1,3,5,7. So let us look by 1. So from here we know that the magnitude is 1 and the angle is R pi. And from this we can define a magnitude condition. So magnitude condition is given by KGH, the modulus is equal to 1. So if you recall back our this can be modified back into K equal to magnitude of 1, magnitude of G S HS equal to 1. Okay, so we know that GS and HS is basically given by, if you recall back, is given by this one. Okay, KGS is equal to this one. So if we were to use this equation back, okay, we know that magnitude this is equal to 1, magnitude of 1 is 1, is basically pi S plus Zi over pi S plus PG. And then if we rearrange this one going up, this equal to this one. Okay, so this SPG is equal to S plus P1 plus 2 and Zi and so on, where S plus P1 magnitude of P2 is called the magnitude from a test point to an open loop of minus P1 and P2, and Z1 is the magnitude from the test point to the zeros of minus Z1, Z2 and so on. And from this magnitude condition we can determine the value of K. Let S be the test point, the magnitudes are N1, M1, M2. Hence the magnitude condition is M1, N1 times N1 equal to K. So if this one, then this, there must be a K here. Okay, there's a K here. K equal to N1, meaning that the K is equal to M1 multiplied by M2 multiplied by M3 and so on, divided by the magnitude of 0, N1 multiplied by N2 multiplied by the N3 and so on. Okay, so this magnitude of, let's say, by graphically in the S plane, this is the S. If this is the pole, so you have M1, M2 up to MM, and this is the 0. From this test point, you can get N1 up to NN. So the other one is the angle condition. As we know that minus 1 is equal to this one, and this gives us an angle of KGH, is the angle of ZI. So this is the symbol of the angle. This is the angle of from the test point to the 0 minus the angle of S point to the poles, where R is 135. And if we expand this one becomes S plus Z1 plus Z2. Remember, this is a symbol of sigma, which is a sum. It is an opposite to the magnitude, which is the product. Okay, so please be sure of this thing. Okay, so because in a complex number, please remember, in a complex number, if you have a complex number of, let's say we give a number of x1 is equal to P1 angle of theta 1. If complex number of x2 equal to P2 theta 2. The product of x1 multiplied by x2 is equal to P1 angle of theta 1 multiplied by P2 theta 2. The product is that the angle P1 multiplied by P2, and the angle is just the sum of theta 1 plus the sum of theta 2. And this is the theory of complex number. And if you have a complex number of division, for example, S1, S2, just for information, this will be P1 theta 1 over P2 theta 2. So it will result into a value of P1 over P2, and the angle is just, since it's a division, is just a different theta 1 minus theta 2. So this recall back, so that's why you have the sum of angle for the zero and the sum of angles of the poles. And if you rearrange back from the theta point here, this will give a value of r pi, which is the angle condition. Alpha 1, alpha 2, whereas alpha and theta is the angle of a poles of a zero to test point, and theta is the angle from the poles to the test point. Okay, now we go into the procedure for drawing a root locus. There's a procedure for drawing. First of all, when you start with a root locus, you must form your characteristic equation. Recall back characteristic equation. If you have a transfer function of this nature, okay, I just remove the h, the s. So for this one, the characteristic will be 1 plus kgh equal to 0. So this is your starting point. And then the second rules for drawing a root locus, the locus is symmetrical at the real axis, meaning that, for example, let's say this is your closed loop transfer function. Consider this is your closed loop transfer function. Okay. So we know that in order to form this equation, we must form first the closed loop transfer function. So if this is the closed loop transfer function, we take the bottom and then we set to 0. This will give us the characteristic equation. Let's assume k equals to 3. Remember, k is the gain. A is the value of the characteristic. K equals to 3, A to 1. So if you find the root, you get this one. So meaning that the root of that closed loop is you have a pole here and you have a pole there. And it is symmetrical on the sigma axis. Okay. Number 3. The number of locus depend on the numbers of open loop poles. Okay.